So I would like to wish you all welcome to our Bioeconomy Breakfast Seminar. We are still having some people joining, so we are trying to keep the timing pretty tight so that this will only take an hour to start at 9 o'clock and end at 10 o'clock. So I think we will start. So for you who have entered, very welcome. We are about to address pulping today with the title Pulping for a Greener World. And we have two presenters that are very experienced in the field that we are looking forward to. And the seminar will actually we'll do it this way, that we will have the presentations from Frédéric Pouillet first, and then we will have the presentation from Claudia Esteves. And after both of the presentations, we'll take all the questions. But as we take the questions in the chat, you can actually pose questions during the seminars as well, but we won't address them until after both presenters have been carried out. So, and I also hope that you would stand to the bitter end of this seminar, because we will like to ask a couple of questions with a Mentimeter where we're using all the smartphones that you are using. So we will try to do that at the end of the seminar. So please don't walk away until 10 o'clock. Okay, with that, I think we should start. And I'd like to present Frédéric Pouillet, first of all. Frédéric is a Frenchman, and he's been working with pulp and paper all his career and has a PhD in bleaching. The presentation that you will give today is more kind of an overview, and we are much looking forward to getting that, Frédéric. So please, the floor is yours.
Thank you very much, Pia. So just let me click on a few buttons, and I think we're ready to go. What do you think, Elena, Pia?
Yes, very good.
Perfect. So I'm Frédéric, I'm working at RISE. This presentation that I'm showing to you today was elaborated with a few of my colleagues. So first of all, Claudia, who is a PhD student with KTH, and we will present some more results at the end of this talk. Of course, with Elisabeth Brandval, who is an expert in the fiber line and pulping, and with Galia, who is also an expert in the fiber line pulping and enzyme aspects. Just a few more words. RISE is now a big company, so we have a lot of colleagues doing multiple things. So it's quite great to have colleagues all around Sweden and to share expertise with them. I'm thinking also of people from the simulation world, like Marta Bielik, and thinking also about the people from MORE. We have now an increased cooperation with them as we are part of the same company, and it really strengthens our competencies. We also have access to pilots, etc. So that's quite a good environment to be working. So yeah, the presentation that I will share today is about our vision for the future of the pulp industry. And more specifically, is it possible to produce pulp with only air and water? And I don't want to spoil the end, but yes, it is possible. Now the question is the quality of what we produce. Since we have a diverse audience today, I will try to mix in between expert level and not expert level, so everybody has something to discuss upon and to ask questions about. So this presentation will be divided in two big volumes because we want to share the story of pulp and paper. So the first volume will be about bleaching, the second one about pulping, and each volume will be divided in a few chapters. Okay, without further ado, I'll start with a long introduction. So some of you might actually think the following: pulp, is it still a thing? And the answer is obviously yes. Pulp, as you know, it's a bioproduct that can be made from wood, from plants, and that finds many, many applications. Of course, paper, packaging, hygiene products, but also textile, biocomposites, bioplastics, etc., etc. So overall, this interesting material has the potential to help in decreasing our consumption of oil-based products. And I'm quite confident when I say that cellulose will be necessary in the future for the manufacture of the bioproducts of the future. So I know that this product is not perfect, that the processes have some drawbacks, and we are going to address some of those points in a few minutes. But we're trying to make it better anyway. So pulp is usually produced from wood, can be produced from other raw materials, and it has three main components. Talking about the wood here, two categories of polysaccharides, cellulose and hemicellulose. So here is a picture of what cellulose can look like. I haven't put the hemicellulose because it's not necessary for today. And then the third component from wood is lignin. So when we make a pulp, so this is lignin. When we make pulp, what we want to have is basically undamaged polysaccharides, or, well, it's kind of a utopia to say that, but we want those polysaccharides to be as good and as long as possible. If you look at the picture, you see the square brackets. It just means that it can be super, super long, and the longer, the better for that. And for a good pulp, we also want to have the low lignin content. Lignin is kind of a glue that is colored, so we basically don't want it for many, many applications. Unfortunately, when we remove the lignin, we also tend to degrade the polysaccharides and cut the polysaccharides, or lose some of them actually. Overall, the industrial practice to produce pulp has right now quite stabilized, and you can find several processes, but one of the main processes is the kraft process. So just to tell you a bit more about what we're talking about, this could be a picture of a bad kraft meal. You got not all of the elements of the process, but some of them. So if we look at this industrial meal, you can basically divide it in two. On the left, you would have the cooking, and on the right, you would have the bleaching. The pulp mill is quite robust as a process. It has multiple products, such as pulp, obviously, but a pulp mill is also a place where you can produce energy and send it to the network. And on the other hand, the pulp mill also has a high consumption of water, and this water that is consumed then has to be treated in a dedicated plant. And the pulp mill also has emissions to the air. So there are a few topics that are a little bit off with the pulp mills, but yeah. I cannot say that the pulp mills are not clean. I cannot say that they are the greenest possible, but I can really tell you that they are getting better and better, and that a lot of changes have happened, have occurred during the last decades. If we look at some specific emissions here, and I can't see it. If you look at some specific emissions, I selected two. Base 100 is 1975, and as you can see, some of the emissions have been decreased by a factor of 50, some other by a factor of 4. Anyway, we are definitely going in the good direction in the decrease of the emissions. In spite of those efforts, the pulp industry is still perceived as a polluting industry. And here are a few emissions that you can list, like the sulfur compounds that are responsible for the bad smell, amongst other things. We have NOx, that are specific compounds that can be involved in smog and in acid rain, so they are heavily regulated. We can talk about the CO2, of course. That's a too big topic for today, but I'd love to be working on that a bit more. Of course, the pulp mill will have effluents, as we said. COD, BOD are two indicators of the quality of the effluent. The higher, the worse. AOX, those are chlorinated toxic compounds that can sometimes, under some conditions, be found in the effluents of pulp mills. And you also have their close cousin, OX, that are chlorinated compounds that can be found sometimes in some pulp products. directly in the product itself. One of the problems with all of those emissions, I mean, I'm not saying that the emissions are too high. No, I mean, compared to 30 years ago, those emissions have never been so low. But at the same time, the very existence of those emissions can pose a problem in the population, and it creates controversies, and those controversies can have damaging effect on the pulp mill, like on the way it runs. Some pulp mill projects have been cancelled because of the involvement of the population. You also have problems when you're renewing the environmental permits because of this increased awareness of the population. And maybe even worse for the pulp makers, some of those emissions actually lead to technical problems. So the industry has been fighting a lot to find ways to mitigate those emissions, try to find a new strategy to recover the air emissions, to burn them again, try to deal with the effluent in another way, try to recirculate, etc., etc. But maybe there's another way to look at those things. And I will take the example of sulfur compounds and of AOX. And we'll make together this table where we will put the emission and the reason behind this emission. Because if you look at the sulfur compounds, the very reason why you end up with emissions of sulfur compound is actually because at the beginning of the process, you add or use sulfur. So this one is hydrosulfide, just the S is for sulfur. And basically, if you look at the table, one of the problems related to cooking is a sulfur emissions. And this sulfur emission is related to, of course, the use of sulfur. If you do the same exercise with the AOX, they appear because at the beginning of the process, well, somewhere in the process, we actually use chlorine-related compounds, namely, in our case today, chlorine dioxide. So now that we've said that, what can we do? Well, you can see that some specific emissions are just appearing because some compounds are introduced in the process when they were not there at all in the first place. So our belief is that if we stop using hydrosulfide, if we stop using chlorine dioxide, we will get rid of the sulfur emissions, at least most of them, and we would also get rid of most of the AOX. So is it technically possible? Yeah, well, with the title of the presentation, you kind of have an idea that yes, we have some ideas about that. So, as we said, we want to have only 2 chemical sources tomorrow. Well, tomorrow, in the future. Water and air. And water and air are quite interesting for us because air contains like 20% of oxygen. If you add a little bit of energy to this oxygen, you produce ozone. Ozone is a really strong oxidant. It's probably one of the cleanest. If you combine water and oxygen together, electrolysis, you obtain hydrogen peroxide. And those 3 chemicals have the full potential basically to pulp and bleach, to create the pulp and to bleach the pulp. So if such a thing existed, it would be called a green chemical island. And if you want to learn more about that, I really urge you to have a look at Alexis Mette's paper. That's quite enlightening on this concept. So somehow, with those 3 chemicals, we can do everything. So in the next slides, I will present you the first volume that is called Green Bleaching, and that will show how to bleach with air and water only. And then I will show a second volume, Green Cooking, and how to cook with air and water only. So please keep in mind that for the moment it's more of a vision, not exactly a clear and established process, but I hope that some of these ideas will question the current practice of the mills. Back to the things we are going to present in the sake of time, as I'm talking a lot, as you can see. We will present the volumes in chapters. The first one will deal with ozone. The second one will combine hydrogen and alkaline stages. For the second volume, we will talk about oxygen, and actually Claudia will in a few minutes, and then we will talk about the pulping strategies. So, volume 1, green bleaching, chapter 1, ozone. There is this common belief in the pulp industry that ozone degrades the cellulose. To tell the truth, it's slightly more complicated. For those of you who know more about pulp, you can have a look at this figure that shows the molecular weight distribution of pulp. And you have two pulps here. You have, it's a tailor-made pulp that doesn't contain lignin and hexane. So it's basically only cellulose. And as you can see, the molecular weight before and after the ozone stage are quite similar. So, and combined with other results going in that direction, we can easily see, yes, ozone does not degrade the cellulose. It's a bit more complicated. So to really understand what happens during ozone stages, new understanding has been developed along the years. Ragnar has contributed heavily to that, myself as well. So I will not go into the details of this figure. If you want to discuss, you can contact me, of course. But the idea is that we have now identified the reasons why ozone can be a bad chemical for pulp. But now that we know why, now that we know why ozone could degrade pulps, it's time to find mitigation strategies, and I will present one to you. This figure shows a brightness against the dP of the cellulose. So basically what you want to have is a high brightness and a high dP, so you want to be in the top right corner. If you only have an ozone stage and an extraction stage, you basically are here on the bottom left. And if you just have a pre-treatment before the ozone stage to remove the hexavalent acid, namely, you end up reaching higher levels of brightness and dP. So that's just one of the examples of the mitigation strategies that you can find, but this one I think is quite nice to see. So I've talked a lot about ozone, so now I'm going to talk about other chemicals. Peroxide. Is peroxide scary? Well, it's not as scary as ozone for the pulp makers, but there is always a little bit of concern that peroxide could degrade the pulp, especially if you put too much of it. This figure shows the degree of polymerization of the cellulose, so the length of the chain, before and after a peroxide stage in some specific conditions here. And yes, there is basically a drop of 300 points of degree of polymerization. If you have a closer look and run some experiments, you will realize that yes, peroxide is totally involved in that, but there are at least two core reasons. One is probably metals or the degradation, and the rest of the degradation would come from carbonyl. So if you just look at this figure from a distance, you would see that the main problem is carbonyls. Actually, it's kind of the problem with peroxide that it can reveal the effects of the other stages. So to well define the conditions of your peroxide stage, you have to address the stages that are usually before. The extraction stages can also have an impact on the depolymerization, and this impact is also partly caused by the carbonyl groups. So there are some protection strategies that also exist that I will not detail here. But if you put all of those things together, you can actually reach pulps of high quality. So in this new graph, brightness against degree of polymerization, the triangles are ECF pulps, commercial ECF pulps. And those squares here were obtained based upon the principle from the first volume. You can see that all those pulps are roughly in the same area of dP, so cellulose quality and brightness, lignin content and brightness. And the conclusion is that yes, it is possible to bleach with only air and water, totally. And yes, the pulps are still of high enough quality. There are even some more recent results that show that those sequences are actually cost competitive. Okay, so back to our little meal. Now that we've addressed the volume 1 of green bleaching, let's have a short talk about the second volume that deals with green cooking. Volume 2, green cooking, and I will briefly talk about the recent evolutions in oxygen delignification, and I'll just give you first the oxygen stage goes between the cooking and the bleaching. It can be considered as cooking, considered as bleaching. The point is, it's in the middle. And you will see in a few minutes results from Claudia. They are really, really interesting and really enlightening, and I will give you a little glimpse into her results. One way to look at those results is to say that you can reduce the cooking time, and reducing the cooking time can actually increase the efficiency of the oxygen stage. Claudia will show you her results, you'll understand. So, I don't want to do a big speech on sociology of innovation, but back in history and during the last century now, several pulping processes have existed. You have the mechanical processes, the chemical processes, in the organosolvers, of course. In the chemical processes, you have the soda cooking, the kraft cooking, sulfite, of course, and I will just talk today about the kraft cooking and the soda cooking. The kraft cooking contains sulfur, as we've already mentioned. The soda cooking does not. It's basically the kraft cooking without the sulfur and a bit longer. Kraft cooking has taken over soda cooking. And the reason why is that kraft cooking is quite good. And it's good because it contains this sulfur. The fact that you have sulfur in the kraft cooking allows for a reduction of the cooking time. Rings a bell, right? And consequently, the pulps are of higher quality, and there is also a higher energy efficiency. But it's not because the kraft process has taken over that the soda process doesn't work. The soda process works. It's just that it's a bit too long and degrades a bit too much. But if you think back about what Claudia will tell you in a few minutes and the short glimpse I gave you, maybe having this soda process but a bit shorter wouldn't be a problem. So basically, my thought is that it's totally time to reassess the sulfur-free cooking processes in light of the new developments based upon the volume 1 of green bleaching and based also on the knowledge developed by Claudia and other people. So the pulp mill of tomorrow could be a bit like this. I'm not saying that it will be kraft, that's another topic. But we hope that the pulp mill of tomorrow would have a green chemical island, that it would be able to produce, just from water and air, all of the chemicals required by the mill to turn wood into pulp. We also hope to have a mill that would have a higher water recirculation, and that's even more possible if the sequence doesn't use chlorine. By its design and thanks to the water recirculation, the water uptake could also be lowered by 50%, which is quite interesting. And in terms of cost, those sequences could be also competitive. So we already have results showing that the OPEX is quite similar. And in terms of CAPEX, we also hope that it would be less expensive. The reason why is that if you remove sulfur, you have a recovery system that is way less complicated. So maybe a bit less expensive, at least not more expensive. Because of the design of the bleaching sequence, it could also be quite a flexible sequence, quite responsive to changes. And overall, the effluent load would also be lowered with lower emissions. And icing on the cake, lower emissions also means that the process would have a higher social acceptance. So, to reach this vision, right now we are involved in several activities. The main one would be the research program that is launched and financed by us, launched by RISE and financed by external partners. And we are investigating fiber line processes. We are also looking at the functions of the cellulose for other modifications. Of course, we are looking into the water quality and its impact on the process and on the concept of water reuse. And we also obviously still look into the existing processes. We also want to develop new concepts for greener bleaching and also new concepts for new pulping processes. Overall, one of the reasons why we think we can do that is because we have some cooperations with the universities. And working with the universities is really a chance to have really interesting discussions and to share expertise, to mutually benefit from competencies and resources to which we wouldn't have access otherwise. It goes both ways. Our aim is really to develop ready-to-use knowledge and ideas, and we also want to prepare the brains of tomorrow for the pulp and paper industry. So right now we have 2 ongoing master students, and we also have Claudia, who is a PhD student with KTH. So the big interest for us with KTH is that it's just next door, so it's quite convenient in a way, and we hope for better and even better cooperation in the future and more fruitful results. So
thank you very much, Frederick. I like your passion for this pulping theme, and I'm sure that there are many many questions for you. And for the newcomers in this breakfast seminar, moderated by me, Pia Wagberg, which I actually forgot to say, and together with Helena Halonen, that is also in the background of this. We would like you all to pose all the questions in the chat. We will, yeah, thank you, Elena. You waved there. I like that. Couldn't do this without you. So anyway, without further ado, I'd like to present Claudia. And we are very international in this pulping area because Claudia actually comes from Portugal. And as Frederick said, you are a PhD student, industrial PhD student with us at RISE, but based also on KTH. So we are very much looking forward to what you can present. I'm wondering if you can share your presentation.
Yes, of course.
I'd also like, while you're doing that, I'd also like to stress the fact that for those of you who have other questions, you can always contact us afterwards, and you will get an email with links to the presentations or the recording of this seminar, and also the unanswered questions. Okay, so Claudia, the floor is yours.
Thank you. So, hello everyone, and thank you, Frederick, for the nice presentation that you gave. So, I'm an industrial PhD, as you know already, and my supervisor at RISE is Elizabeth Brandval, that was already presented by Frederick. And at KTH, I have another two supervisors, Elena Svestianova from Fiber and Polymer Technology, and Søren Oslund from the Mechanical Department. And my PhD is about using oxygen in a more efficient way and to look at the oxygen in a different highs that are not the same as now people look at that. And yeah, so today I will just focus on oxygen delignification and the fiber charges that are the main important thing in this subject. And then I will go quickly through the methodology, results, and conclusions. So as Frederick already said a little bit, our purpose is to look at oxygen and also look at the kraft pulping in a different way to understand what are they doing, what is the difference between one and the other, and what can we do when we do a shorter kraft pulping or do a longer oxygen delignification, or vice versa. And so the main point here was to terminate the kraft pulping in a higher lignin content and then perform oxygen delignification, and to understand what are the advantages for that. And first we thought about that because terminate kraft pulping in a higher lignin content, it is known to increase the bleachability of the pulp because we are producing less condensate units so that are resistant to the bleaching steps. So we can have some advantages to that besides reducing the energy, for example. And by doing oxygen delignification, we can decrease the amount of the bleaching chemicals used afterwards, and we can also decrease the effluent pollution. And by doing oxygen, we also consume less energy because we use a lower temperature when we compare to the kraft cooking. And the most important in this case is to increase the fiber charges because they are the main role here. And in overall, we could have, by doing this, by shortening the kraft pulping into oxygen, we could have a more environmentally friendly technique that can improve the mechanical properties and can also reduce the refining energy consumption. So we have a lot of benefits. And besides these benefits, we can also look at oxygen is a more selective way to do the lignification when we compare to the bleaching chemicals. And it's already a well-established technology in the major part of the pulp and paper industries. So it's not so difficult to manipulate if we want to do a shorter kraft pulping and a longer oxygen delignification. It's not so difficult to implement. And we can increase the total fiber charge, and this will lead to the increase in the mechanical properties of the paper. And we have already some studies that suggest that. So I'm talking about the fiber charges, and the fiber charges are the acid carboxylic groups present in the pulp fibers. And these figures here are just a representation and an illustration about one fiber with not so highly charged content and the other fiber with a lot of fiber charge. And what is doing the fiber charges, this increase in fiber charges, is increasing the swelling of the fiber. And by increasing this swelling, we will also increase the conformability of the fibers, as we can see more or less in this figure here. And by doing that, we increase the bonding area between the fibers that will lead to an improvement in the mechanical strength. So the fiber charges are very important in this case in order to modify the pulp properties. And this is another illustration, and I will try to explain you what is the basic behind this. So this is a representation of uncooked wood, that the blue dots represent the fiber charges. And the fiber charges are mainly present in lignin and carbohydrate. So in the beginning, we have a lot of fiber charges because we have all of the components in the wood. But then when we perform a kraft cooking, what we will do is to remove a lot of the lignin and some of the carbohydrates, unfortunately. So by doing that, we remove a lot of fiber charges as well. One way to overcome this is to perform a shorter kraft cooking. So in that way, we don't lose so much lignin and carbohydrate. We preserve some of the fiber charges. And then we do oxygen delignification. By doing that, we increase the fiber charges by lignin and carbohydrate oxidation. And in these two samples, we have the same lignin content, but one has much higher fiber charge content than the other one. And the difference will be in the swelling, because this one will be much more swollen than the other fiber. This will increase a lot the refinability of the fibers. That will help the conformability, like I said, and the strength. While the other one, without the oxygen and without so much fiber charges, will not have the same properties, the same good properties. So our approach that I will show you here today, we did others, but this is just an example. We did 3 different trials for the same lignin content that we call kappa number. In this case, is kappa number 30. So we did 3 different kraft pulpings with different times. They are the same, but they have different times. And then we have the oxygen delignification here, that we did a longer step and a shorter one. So the difference here is the starting point from the kraft pulping. And then we will compare and we will try to understand what are the differences between them and what we can gain with one or the other. And we did several characterizations techniques. I will not show all of them. This is just a few. So we did chemical compositions to understand what is the chemistry of the fibers, the lignin content we saw through the kappa number measurements, the total and surface fiber charge, and the viscosity to see how much we degrade the carbohydrates. And these are the mechanical tests. I will just talk about the tensile strength, but we also did short tensile strength and ZD strength. And we also look at the morphology of the fibers. And we also look at the fiber swelling by analyzing the water retention value and the fiber saturation point. So the methodology, like I said, is 3 different kraft pulpings, and then we perform 2 oxygen delignifications with different times, and then we do PFI refining, we do lab sheets, and then we test the mechanical strength of the paper. And in this graph here, I hope you can see my pointer, we have the total fiber charge and the kappa number. So you can see this line here. That is when we start from the uncooked wood, so in the kraft pulping process, that we have a lot of fiber charges, as I said before. But then when we start to remove lignin, we will lose a lot of these fiber charges because we are removing lignin and carbohydrates. So the tendency is only to decrease with kraft pulping. And then we have these 2 trials here that are from the oxygen, one starting from this kappa number and the other one starting from a higher kappa number. And in this case, we got an increase of 80% of the fiber charges when we use oxygen delignification and when we look at the same lignin content. While for the other one, we just got an increase of 46%. It's not so high as this one, but one thing that we can take from here is, of course, oxygen can increase the fiber charges, but the way and the amount of the increase is different depending on how you do the process. So now we look at the tensile strength. So we will compare to this kappa number. So for this kraft cooking, we got this tensile behavior along the PFI revolutions. And then we will compare to the oxygen delignification that we did starting from here to kappa 30. And in here you can see that we didn't have any improvement in the mechanical strength. Even if we have higher fiber charge, we didn't got any improvement in the strength. And then we did another trial starting from a higher kappa number to the same as the other 2. And in here you can see that we had an increase, a significant increase of around 14% in the tensile index. That is quite interesting. And you can ask, what about the density? Because tensile strength is depending on the density. So when we look at the tensile index along the density, you can see that we have a tensile index improvement of 6% for the same sheet density, but with less refining energy. So we are comparing this point here from the kraft cooking that has 4,000 revolutions through this one that is an oxygen delignification with similar tensile strength, but with just 2,000 revolutions. So we got around 50% of energy savings when we use oxygen delignification in a way that have increase, that has a higher increase in fiber charge. And the swelling effect, that is also a very important thing to see. We have the graph with the water retention value and the PFI revolutions. So it's clearly you can see clearly the difference between this one, the black, that is the kraft cooking, and then the other one that we did a shorter oxygen delignification. We get a slightly increase. These values here are related to the total fiber charge that we got from the fibers. So the big difference here is to look at this one that had the 80% of fiber charge increase. And you can see the increase in the water retention value is much higher than the other one with not so high fiber charges. So the difference will be this one will be much more swollen than this one, and it will have that properties that I said in the beginning. And also is interesting to look at the tensile index and the Schoper-Riegler degree. In this case, if we look closer, we have similar tensile strength with the same Schoper-Riegler, but with much less refining energy. So we have the 4,000 revolutions for the kraft cooking, and then we have just 1,000 revolutions for the pulp. when we use oxygen delignification. And besides that, we also look at the oxygen delignification after a high alkali impregnation. And we can see that we can have even more savings. One of my supervisors, Elizabeth Brandval, has shown this, that we can increase the yield from the kraft pulping when we use a high alkali impregnation instead. And we did the same. We did the standard impregnation and the high alkali impregnation, and then we did the oxygen delignification to see if we can have the same improvement in the mechanical strength. And in here we have the tensile index along the PFI revolutions, and we have along the density. And we saw the same. So these two lines are referenced just for the kraft pulping, a standard and the high alkali impregnation. And these two are referenced to the oxygen delignification. So we get an increase, not so high as the other one, but we also get an increase. And when we look at the density, we see the same. So we have the same tensile, but with lower refining energy. This will mean that we have around 1.2% of yield improvement in total yield. We can have around 3% of wood savings. That will result in €1 million per year of savings when we look at the average Swedish production of 700 tons per year. So I think there are very interesting conclusions and very interesting points that when we look at oxygen delignification in a different way, we can have different results and a lot of savings. So as a conclusion, we can see that oxygen always increases the fiber charges, but not always we get the mechanical strength improvements. So this will depend in the way that we will do the oxygen delignification, if it is starting from a higher kappa number or a lower kappa number. And what we saw was if we start from a higher kappa number, a higher lignin content, we will have a much more ability to increase the fiber charges in a much more percentage, while if we just start from a lower lignin content. So this will depend on the oxygen conditions. And this increase in fiber charges will lead to an increase in the fiber swelling. And this increase in fiber swelling will lead to a better refinability. And therefore, we will have much higher tensile strength. And besides all that, by doing this approach, we can reduce the energy by reducing the kraft pulping step. We can also increase the yield, and we can save energy by getting the same tensile index, but with lower refining energy. So I think it's interesting to look further into this and to be able to get more knowledge about oxygen delignification together with kraft pulping and together with the rest of the things. So please, if you have any questions, feel free to contact me. You have my email if you want to contact me afterwards. And I want to thank my team and acknowledge the STFI funding because they finance my PhD. So thank you very much to all of you.
Thank you, Claudia, for a very nice presentation. I see that we have some questions in the chat, so I'd like to go straight to them. First of all, we said that we would take all the questions right now. So the first question actually goes to Frederick from Lisbeth Galbraith, who asks about the What about, is anything known about the properties of the lignin and the hemicellulose during the water and air only pulping? And she says that she means that will these fractions be usable in other ways than heating, Frederick? What do you say?
I definitely hope so. I mean, if we pulp with only air and water, it means we don't have sulfur. And if we don't have sulfur, we can obtain an interesting lignin, I guess. Like in the black liquor or its equivalent, it would be a low molecular weight lignin without sulfur. So it could open up a lot of applications. Like one of the problems met when you use lignin is that it like the current kraft lignin contains sulfur. So you've got either to remove the sulfur or you end up with a product that can have a little smell. So yeah, people from lignin would kill me if they heard me, but that's, yeah, high level. Anyhow, so without sulfur, we would have a sulfur-free lignin, which could be quite interesting when it comes to the use of the hemicellulose and its extraction. Well, we still want to take advantage of the things that Claudia has demonstrated. So we would like to keep some of the hemicelluloses inside the pulp. And one of the objectives is also to make pulp for paper applications. So we still want to have some of the hemicelluloses. That being said, it doesn't mean we cannot try to find a way to have other hemicelluloses at one point in the process.
Okay, well, Frederick, you have another question here, and that has to do with, it's from Samsolaxov, that wonders about the intake of water, or the lower intake that you were talking about. How much water intake would it be in the future? Can you look about to see in the future? And then also, what about the properties of TCF bleach pulps? Are they the same as the properties for ECF bleach pulp?
So first aspect is on the water. On the water side, well, it is usually said that the mills, the current good mills would use 15 cubic meters per ton. Well, this value can be the double, triple in some cases. There is one mill that is really doing well with, I think it's 7 to 8 cubic meters per ton. So, I mean, the idea of 50% of reduction of water doesn't come from nowhere. It's not like, let's divide it by a number. It's based upon the inputs of water that would be required in the process. So I would say it's at least 50%, depending on how well the flows can be recirculated. There is still this opportunity of having internal water treatment. There is a paper from RISE on that topic that is, and another one from Andres, I think. And yeah, it depends on the water strategies of the mills. I mean, I would be really happy if all the mills or most of the mills went below the 10 cubic meters. That would be quite already an achievement, I think. I hope I answered the question on water. And then it was about the yield and properties of TCF.
Yes. Is there a difference in the properties between the ECF and the TCF?
Difference in properties, let's say that back in 20 years ago, yes. Now today it's less and less clear. And I know there is an ongoing PhD work in Grenoble on that very topic, like using the last developments of TCF to try to see the real impact of TCF bleaching on the fibers. There is one thing when comparing TCF and ECF, and it goes for the mechanical properties. It's also true for the yield. A lot of mills that would have a TCF sequence would actually have a longer kraft cooking to reduce even more the amount of lignin, so that bleaching would have to do less job. So comparing the properties of ECF and TCF today is a bit challenging, but if you want to know about the mechanical properties of the new developments, then you might have to wait a couple of months. But the idea is that those pulps should be good enough for paper production.
Okay, Great, thank you. Yet another question here, Frederick. We're grilling you with a question from Kiran, who is wondering about the water and air cooking that you were talking about. Is it a dissolving grade wood pulp? And if yes, what would be the percentage of lignin content?
So we have not actually made that pulp yet. And most of my life has been about preserving the degree of polymerization of the cellulose. So most of my life has been about making pulp for paper uses rather than dissolving grades. But I mean, it kind of depends on the strategies that would be adopted. Soda cooking, long soda cooking could, for example, change quite heavily the outcome of the process. So as such, as I would say that the green bleaching results that I presented that were coming from my PhD work financed by a couple of companies, that those results can be used for paper grade. I mean, dissolving grade, the chemicals would still be good, but it's looking at things through another angle.
Okay. Thank you very much, Frederick. And now, Claudia, there are some questions for you as well. How much was zero span affected by different pulping processes?
We didn't did zero span. We did short tensile strength, and by that we didn't saw any difference between the kraft cooking and the oxygen delignification, with not so higher improvement in the fiber charge. But we saw the higher short tensile index for the higher fiber charge sample, the one with the biggest one. But the rest was pretty much similar to the tensile index results with the tensile strength normal test.
Okay. Thank you for that. And there's another question, Claudia, for you. Did the wood saving remain after full bleaching of the pulp? That's Åsa Norstedt who is wondering.
Yeah, we didn't look at the yield for fully bleached pulps. We are doing that, but with slightly a different approach. So with the high alkali impregnation, comparing high alkali impregnation with the standard impregnation. And in that case, yes, the yield is still there after the fully bleached sequence. But between just the kraft cooking and the normal bleaching sequence compared to the oxygen with a very high fiber charge, we didn't look at that yet.
Okay. You have another one here, Claudia, and that is Michel Petit-Conil. That one is if the WRV is increased due to better fiber swelling, what is the consequence on the paper sheet drying? Would that be more difficult to dry?
Yes, I would say that it could be more difficult to dry. Of course, we didn't test that yet, but we also have to look at the pulp fibers after oxygen, not only for the paper production. We can also look at the fibers for other productions where the fiber swelling is important, and where the fiber swelling is even more important than the drying section, because we can do products with oxygen fibers for other applications. So the sheet drying will be difficult, I would say, but maybe it's not a problem if we think about in other applications.
Okay, thank you very much. I see no further questions in the chat. There's still room for one or two more questions. But with that, I'd like to thank you very much again, Frederick and Claudia. I thought myself that was very interesting presentations, because somehow we are surrounded about with sustainability issues and climate change and all of that. And I think what you are presenting now from the pulping point of view is very interesting. How can you approach the greener thinking technically on the pulping side? I at least think that's very interesting. So before we go into the final part of our seminar, I'd just like to call upon Helena to see, because we are continuing with our breakfast seminars, and the next topic is actually on molded pulp, isn't it, or wet forming? Right, thank you very much. So it's 3D formed fiber packaging. If any of you who are present today are interested in this topic, you are very welcome to register for our next seminar that will take place in September.
And sorry, Pia, I would like to add that it is more than molded pulp, I believe.
Yes.
Yes, so 3D formed fiber packaging.
It's a kind of a it's a broad topic that has a broad terminology as well, right?
Yes.
Yeah. Okay, so by that, before you all go to your other, if you could stop sharing that screen, I will try to share my screen, because we'd really like to get your input on, let's see, screen 2. Yes. To get your input on what you have been experiencing today. So therefore, please take out your smartphones and go to menti.com and put the code in. And we have some questions for you. It seems like this is kind of stuck. Let's try it one more time. There.
You can try your keyboard as well with the arrows.
Yeah, I'm trying.
Really?
Yeah, it's Mayday. Let's take this first one. Look, they're already answering. Wonderful! What a nice audience. Because we are trying to get some input from you on your experience on the presentations, and if we could what you thought about today's seminar. And your input is very valuable for us, because Helena and I are trying to keep track of this. So please answer that. And then we only have 2 more questions for you. I think I could go on to the next slide, Helena, while everybody is answering, right?
Yeah, you should do that.
Yeah. So continue to answer our questions. And yes, look at that. You have already answered. Because this is also interesting for us to know exactly where you got your information from. We are always trying to improve our format. And in that work, we are, of course, up to your feedback, positive and constructive criticism. And also we are very much open for new ideas for future seminars. So if you have any ideas, please enter them here. Hope that innovations can be introduced in the industry in near future. Yes, so do we, right, Frederick and Claudia? And that's what we are actually at our institute. I mean, that's what we are working for, to transfer academic research into implementations in the industry. Okay. So there's 1 minute left to go, and I would like to take the opportunity to just say thank you so much for everybody who has listened. You will get a follow-up email, as I talked about earlier, and we will give you some tips on who to contact in what area from our part, so that you can keep on the discussions with our researchers. Okay. So with that, we say thank you, and we will see you hopefully in a future breakfast seminar. And thank you so much again, Claudia and Frederick, for your input or your presentations.
Thank you.
To everyone.